Good afternoon. This is Dr. Manis once again. Hey, this is just a quick little video on K prime versus K. If you don't know what that means, basically, what do you do when the equilibrium constant is derived from a previous equilibrium constant? What this deals with is when an equation has been altered. There's good reasons for why chemists alter equations. Sometimes it's just practicalities. It just really depends upon what you're doing. I gave a groovy little example right here about uranium. I like it because there's uranium in it. How often do you get to talk about uranium? So basically, just to work this through, look at the uranium. You got uranium oxide plus chlorine gas makes the uranium chloride thing plus O2. Can you write that equilibrium expression? Of course you can. Products go on top, reactants go on the bottom. Don't forget your exponents. We're ignoring the U3O8 because it's a solid. But if you wrote that equilibrium expression, it'd be 2.931 times 10 to the negative 13th. So compare that to the ones down below. These equations, this question like right here, stink, always intimidates students. But then you realize what you're doing and it's not so bad. So don't be too intimidated right off the bat. I did a lot of the work ahead of time because I didn't think you'd want to watch it. Basically, let's look at the green one. The green reaction is the same reaction except it's in reverse. This reaction right here is the same as that, but it has been flipped. And so doing, the green K prime looks like the yellow K prime flipped. And that's exactly what it is. Instead of, if it's always products over reactants and you switch which ones are products, which ones are reactants, you're going to flip the ratio. So all you have to do is plug in and think, hey, it's going to be the other K to the -1 because -1 means flipped. So we could plug in our value of K prime, our value of K into K prime, and flip it. And if you get 2.931 times 10 to the negative 13th to the -1, remember that -1 power right there, that means reciprocal. So just take the reciprocal on your calculator and you will get the value of K prime to be 3.412 times 10 to the 12th. Alrighty, let's look at this peachy tanny guy over here, whatever you call this color. All right, it's the same equation, but if you notice, the coefficients have been altered by a factor of 3. To go from here to there, there's a 3 times the amount, okay? So if you look at my first line there with the equal expression of k, now we can factor out that exponent of 3, that factor of 3 to the exponents by writing this expression. I put the yellow inside so you can see that, hey, this guy is right there. So k prime looks like the old k, but to the cube power, that factor of 3. So just like before we plugged in for the reciprocal, we're going to plug in the k again. Right here is where I am. Plug in the value of k, cube it, all right? And you will get some giant value of k that 2.518 times 10 to the negative 38. It's not a giant. It's giant in fact that it's big, but it's really, really small. Big exponent. Small exponent. Anyway, what we want to generalize from this is the whole idea behind it. You need a general equation to go from. Well, the derived exponent, k prime, prime is derived, is the old k to some n power. N is negative if it's flipped, and then it's also the factor by which things were multiplied. So up here, there's a factor of 3 because everything was 3. That is negative because it was flipped. So n is going to be negative if you flip. If we did both of it, it'd be to the -3. So just plug in your value of k, throw in an exponent. Don't be intimidated by it, and just hit solve on your calculator. You'll be good to go. All right. So you're smart enough to handle this. Like it, love it. Have a good day.